Welcome to Chapter 4, Sections 7 and 8, Optimization. And in this section, we're going to continue to optimize functions, meaning finding the absolute maximum and absolute minimum. But we're going to look at more applied situations. In the past, in Section 6, we were given the function and we had to maximize the function or minimize the function, which is optimization. And in this section, we're not going to really have the functions. We're going to have to create these functions based on situations. So let's take a look at an example. So let's say we have a piece of wire of length L and it's bent into a shape, a rectangle. And we want to know what dimensions are going to produce a maximum area. Okay, so we write there the keyword maximum. That's telling us we want to maximize something here. So we have to come up with a function that we will maximize. Well, since we want to maximize the area, we need an area function. Okay, and we're going to call that function A, and we're going to say it's a function of x. Okay, L is our length of the wire, and that is a constant, and that's one thing to remember here. We're going to treat L just like we would any other number, like if it were the number 3, 15, whatever it may be, we're going to treat it just like that. So we know the derivative of L with respect to x is 0, and that's important. Okay, now what is x? Well, we're going to call x one of our dimensions of our rectangle that we're going to make here. Now, the other dimension is 1/2 of L minus x. And this might be a little tougher to figure out where this comes from, but I'm going to leave it up to you. It's just a little algebra. If you call the other dimension, say y, you know that 2x plus 2y has to equal L. Well, if you solve for y here, it's 1/2 L minus x. Okay, so that's what we're going to write it as. We're going to write it as an expression of 1/2 L minus x. So that way we only have one variable that we're concerning with. X is our only change. Now before we move on, let's talk about what is our domain of x. And that's important here for all these optimization problems. We create our interval because x is some number. It could change, but we know it can't be any number under the sun. It's not going to be some open interval from negative infinity to positive infinity because we have constraints on x. X has to be bigger than 0, so it can't equal 0 because if it equals 0, then we have no area and we just have a length of wire. And x at the most can be 1/2 of L. And you might ask, where did that come from? Well, that comes from the fact that L over 2 minus x has to be a positive number. And so if L over 2 minus x is greater than 0, well then L over 2 has to be greater than x. Okay, because we can't have a negative length of a side. So that's got to be true. So there are constraints. That is our interval that we're going to use here. We're going to use the closed interval from 0 to L over 2. Okay, now we still have to write our function that we're going to optimize here. Well, we're dealing with a rectangle, and the area of a rectangle is just the length times the width. So our function is x times the quantity, L over 2 minus x. So this is our function here, and we're going to go ahead and distribute and say that we have L over 2x minus x squared. And that is A of x. And so we want to optimize this over the interval 0 to L over 2. So we need to take the derivative. Just like any other optimization problem we've done, take the derivative, find the critical points, check critical points and endpoints, see what gives us a max. And that's what we want here. We want a max area. So A prime of x is going to be equal to L over 2, because remember, L is a constant, so we don't need a product rule here. Just because L is a letter doesn't mean it's a variable. Okay, so L over 2 minus 2x. Well, when we set this equal to 0, we see that, okay, well, what's going to happen? What x is going to give us a 0? That's x equal to L over 4. And so that is our only critical point here. And we need to check, is this a maximum or is this a minimum? Because there's a chance that it actually could be a minimum, in which case our endpoints would yield a maximum. So we have to check into our original function if we have L over 4. So what is A of L over 4? Well, that gives us L over 4 times the quantity L over 2 minus L over 4. So this gives us L over 4 times L over 4, because the difference of 1/2 L, 1/4 L is 1/4 L. So that gives us L squared over 16. Now, that in fact is our maximum. So we are maximum at the point L over 4, L squared over 16. Now, how do we know it's a maximum? Well, let's check our endpoints. If x is 0, well, then our area is 0. If x is L over 2, then once again our area is 0. So therefore, this is our max. L over 4 gives us our maximum side length, which means that our maximum area is L squared over 16.